This is about determinants and cross products. Specifically, it's coming at it from a little bit of a different angle from what most presentations of the cross product are about. Often you see the cross product defined first and then the determinant and the idea of a triple product or the volume of a box coming out of that. That's backwards from the way it really should be. And so this is a presentation that's a little bit different. You can read what I've written here. This is from a written presentation that I'm going to be going throughout this video. So you can pause it and read it if you want. But what we know, what we're assuming we know, is that we know the idea of the determinant of a 3 by 3 matrix, really an n by n matrix, but in this case we're always going to be doing 3 by 3. There's something special about that. And we are thinking of it as 3 row vectors, A, B, and C. And we're thinking of this as calculating the oriented volume of the box. So oriented means that this box in this order is a rotation or deformation of kind of the standard box with ijk. That's one way to say it. Another way to say it is it satisfies the right-hand rule, that if your right hand is B and your fingers are C and your thumb is A, then we get a positive number. Okay, so that's what we're supposed to be assuming. Black's not working too well, about the determinant. And I claim we can get the cross product out of that without too much work. Assuming we know a little bit more about algebraic properties of the determinant as well, I should say. Okay, so here's the situation. We actually only have the 2 vectors B and C in R3. And it's definitely just in R3, 3 dimensions. Those two together, ooh, I forgot the last strut of this box here. That's why it looks so weird. Okay. Those two together don't create a box. They do specify, unless they're collinear, which is a special case we'll deal with eventually, they do specify a plane that they lie in, but they don't actually specify a box completely. So the idea, as I say over here, is let's suppose we have B and C. Let's prepare as much as possible to calculate the box, the volume of the box formed by A, B, and C before we actually get A. And there's a way to do that. What we can look at is the formula for the determinant called the cofactor formula. And this really came out of some deep properties of the determinant, mainly multilinearity. And it says that we can calculate that and separate out the influence of the different components of A. So it's A1 times the determinant of this 2 by 2 minus A2 times the determinant of the 2 by 2 we get from these two and these two, deleting the middle row, middle column and the top row, plus A3 times this guy. And the trick, the real heart of this is just to observe that that's a dot product. It's a dot product of exactly the vector A, A1, A2, A3, with a vector that would have this component minus this determinant as the second component, and this determinant as the third component. In other words, this vector. Okay, so that's cool. Let's define this, and remember, this is only coming from the B and C information. Let's define this to be an interesting combination of the vectors B and C. Okay, and so we're going to define this to be the cross product of B and C. There's even a nice way to write it in terms of determinants. This looks exactly like this formula, except with the A1 replaced by I, the A2 replaced by J, and the A3 replaced by K. Just kind of making them placeholders for that dot product to be done. So formally, we can write it this way. We can say, if you apply the cofactor formula to this 3 by 3 matrix, even though it's a kind of a weird object with numbers in these 6 slots and vectors in these 3 slots, if you apply the cofactor formula to it, it totally gives you exactly this formula. I times this determinant, J with a minus times this determinant, etc. Okay, so there's the explicit formula for this interesting combination of B and C that we're going to be investigating. Here's a nice way to remember it in terms of a kind of a weirdo 3 by 3 determinant, and we're going to call that the cross product. Okay, so here's the fundamental definition, and that is that if I want to take the oriented volume of a box, we already knew this formula for it, and we know a lot about how to calculate it. It's the determinant of the 3 by 3 matrix with the honest A, B, and C. And now we're defining B cross C to fit into this equation. It's this funky vector that when you dot it with A, you recover the cross product, or the three-dimensional determinant, rather, 3 by 3 determinant. And here's the calculational formula, the shorthand that we get for that. So this is how we're going to calculate it most of the time from components. But this is really the heart of it. But the meaning of the cross product is it's a vector that you create out of two vectors, b and c, so that when you then bring a third vector in, it's very easy to calculate the volume of the resulting box. And all of the properties of the cross product can come out of that. Okay, so you might want to read that if you want. That's kind of a more textual presentation. The idea is we want to get that from that geometry to what's going on. So let me rewrite it over here. I left that open too long. Left it uncapped. Let's try red. The determinant, which we know is oriented volume, is this guy. It's a little bit of a weird definition, but it's an incredibly nice property to have. And so this is the same thing as the oriented volume of the box. And we want to go through what we can get out of that. Okay, so as with a few of my other videos, what I've done is I've taken an in-class investigation and I'm going to work through it. And a really good way to get a lot out of this, if you want to work with this, is pause the video from time to time and try to do the exercises before I do them. Okay, so here's the first thing. We can figure out just from the geometry what direction B cross C must lie in. Okay, let's see if we can do that. And I need a tissue to erase this. Okay, I'm going to leave the... Let me actually erase the box. And I'm going to draw a new one here. Okay, so we have B and C lying in some plane, making a parallelogram. Okay, and I don't have the vector A yet. Okay, and here's the suggestion. To figure out what direction the vector B cross C must lie in, we don't know a lot about it besides this magical property that dotted with any vector gives the determinant, the oriented volume of the resulting box. And so here's a suggestion. Well, what if we picked A to be something special? It's a very common thing. If you've got a rule that works for any A, let's pick it to be special. Let's pick it to be equal to B. Okay. Well, so B dot B cross C, that should be the volume of a box formed by B, C, and B itself. Instead of having A go off in this direction and have a full three-dimensional box, it's collapsed to all be coplanar, and that should have 0 volume. So that should be 0. Okay. For B here, what about if you take the oriented volume of the box formed by the vectors C, B, and C? Okay, well, that's supposed to be this vector, which we're still trying to understand better. And now, instead of A going up in this direction, it has folded down and become C. They're still all coplanar. That should still have 0 volume. That tells us a heck of a lot about what direction B cross C must be in. Because what does the dot product of two vectors being 0 mean? It means that B cross C is perpendicular to B and to C. If you know anything about cross products already, that should be familiar. I'm assuming we don't know that yet. And so this is a really cool thing. So another way to say it is, let me clean up this picture a little bit, is that we have whatever this plane is that's spanned by B and C, and the dot product then, or the cross product of B and C, is perpendicular to that. It's either up here or maybe it's down here, but it's along this line. Okay, and so that's our conclusion for this first exercise, is that B cross C must be along the line perpendicular to the plane spanned by B and C. Okay, so we've got the direction information except for an up-down thing, and that's going to have to do with the right-hand rule. Okay, well, that'll have to do with the oriented nature of oriented volume, the positive plus and minus sign. But let's not worry about it right now. Let's look at the magnitude. Okay, so let's see. I still want this, because that's our fundamental fact, but we're sort of done with that. Okay, so now I am going to actually go back and use a general A. I don't want to use a special A equal to B or C anymore, because those were just 0 volume boxes. That's never going to tell me anything about magnitude. Okay, so here's A. Okay, so here's the box. Okay. And I just want to compare this to my ordinary knowledge of volumes. Okay, so let's look at this in detail. So given a box made with vectors A, B, and C, let's treat the parallelogram here as the base. And then we know that our geometric formula from way back when, volume is the base, we're going to call that area A, times the height. Okay, so that's all that is in the first part. And again, this is a good place to pause if you want to try and do this yourself. It's really small steps, nothing super complicated. Okay, now let's see. Show geometrically that h is the magnitude, the absolute value of the component of A in the direction n, where n is a normal vector to the plane spanned by B and C. That's a big mouthful, but it's not a difficult picture to draw. We take this plane. We already know that when we have planes, that normal vectors are really useful. Okay. And what does it mean to take the component of A in the direction of n? It means just project it and take the magnitude of this guy. And since I'm taking the absolute value, I don't care whether it's plus or minus. It's just exactly the length of this segment. Well, hey, guess what? That's exactly the definition of the height of some sort of slanted object. The height is just how far you have to go up perpendicular to the base to reach the top. Okay, so the volume is now the base area times that absolute value of the comp of A in the direction n. Okay, and now we know there's a formula for this in terms of dot products. Okay, it is just A dot n divided by the magnitude of n. Okay, and that's already positive, so it doesn't need the absolute value. Okay, so we've got one thing, which is the oriented volume of the box has to do with this dot and cross, and we're trying to analyze and figure out what this is all about. Okay, and now here's another formula for the volume. This doesn't have the orientation in it anymore. Okay, so let's just take the absolute value here as well. Okay, so these guys are supposed to be equal. Notice they both have an A dotted with something. So let's rewrite this as A dotted with n times A over the magnitude of n. That's interesting. So this guy is, let's see. So this is, let's phrase it one more time. I just want to make it more clear. Okay. So what's special about this vector? It's a unit vector. That's just pure direction information. Okay. So this guy is a unit vector perpendicular to the plane of spanned by B and C with magnitude A, the area of the parallelogram. And this is supposed to be equal to this guy. Always, no matter what the A is. Well, the only way that's going to work is if B cross C is, as we know, a vector perpendicular to the plane of spanned by B and C with magnitude equal to the magnitude of this guy, which is exactly A. Okay, so what's the upshot of that? A little bit of a complicated chain of reasoning. But the upshot is that the magnitude of B cross C, this vector has to, we know it's in the same direction as this guy. This says it's normal to the plane. This gives the magnitude as the base. And we know it has to have the same magnitude. So it's just the area of that parallelogram spanned by B and C. That's another fundamental fact about the cross product. And it just comes from a very basic issue of how you find the volume as base times height, and the fact that that matches up when we look at dot products and components with this guy. Okay, so that's this exercise. Okay. And then a corollary of that is, I think I can take this away for now, that if we just look at this thing from a top view, kind of losing our green there. Let's try blue. These things run out really quickly. If this is B and C and this angle is theta, then we can look at geometry again to say, oh, I know. The area here is just how long. Now, this is the base of a parallelogram, not just a three-dimensional box. times the projection of c on the direction here, and that's just going to be bc sine theta. Okay, and that is the magnitude of the cross product. So in a minute I'm going to stop, but let me just note something that's right at the bottom, this warning here. Okay, this is a vector. B cross C is a vector. It's got all kinds of interesting uses as a vector, and its direction is quite interesting. In three-dimensional space, no matter how B and C are oriented in three-dimensional space, the cross product is going off perpendicular to that, and so it has very interesting direction information. So as I say in this note here, it's very easy to get mixed up with that and think, oh, I think the cross product is this quantity, especially since that's so similar to this, which is really correct. It says the dot product, since it's a scalar, really is exactly just this formula. That's the geometric formula for the dot product. The geometric formula for the magnitude of the cross product is very similar looking, but with a sine instead of a cosine. Okay, but the cross product has a lot more information. It's actually a vector. Okay, so in the next video, I'm going to go on and derive some more properties of the cross product.